In the previous video, we established that charged molecules, the interaction between charged particles, is the origin of intermolecular forces. We discussed ion-ion, which is a fixed positive charge and a fixed negative charge. And we also discussed dipole-dipole, which is the interaction between polar molecules, or the positive dipole of one molecule interacting with the negative dipole of another. The third type of intermolecular force that we learn about is when you have non-polar molecules interacting. Okay, so these are known as dispersion forces. Or you might have heard them as London dispersion forces, or perhaps you've heard of them as induced dipoles. Any of these are acceptable ways of describing non-polar interactions. So thinking about how two non-polar molecules interact according to Coulomb's law is really, really difficult, right? So for Coulomb's law, what we need to be true is to have a positive interacting with a negative. And for non-polar molecules, that doesn't happen, okay? So this is where this idea of induced dipoles come in. So think about it this way. You have this molecule, and let's make it really simple. You have this molecule that contains 2 electrons. Okay? These electrons are evenly spaced, and since they're evenly spaced, they cancel each other out. That's why it's nonpolar. Okay? But remember, electrons are not stationary. They're mobile objects that are always moving around, right? So let's just imagine these electrons, they're both rotating in this counterclockwise fashion. Okay, so it's possible to have an instantaneous dipole, right? So what that means is that for a very, very, very short amount of time, maybe one of these electrons is moving a little bit quicker than another one. So we have both electrons situated on one side of the molecule, giving this molecule a partial negative and a partial positive. Okay? It's important to recognize that this is not a permanent dipole. This is a very short-lived temporary dipole that will collapse immediately unless stabilized by something else. Okay? So this molecule has a dipole that's induced by something else, and if it happens to come into contact with another polar molecule, it can in turn induce a dipole in this next molecule. So it can push the electrons of this second nonpolar molecule to one side or the other, giving it a temporary dipole as well. So molecule 1 can induce a dipole in molecule 2. And now we have these polar ends, right? So a negative end and a positive end that can now interact. Okay, so that's the origin of the intermolecular force that can occur between nonpolar molecules. All right, and these are known as London dispersion forces or induced dipoles, and they're weak. Okay, so each dispersion force compared to a single dipole-dipole or a single ion-ion interaction are very weak. However, collectively they can be really strong. Okay, so induced dipoles or London dispersion forces are present in all molecules. Every single compound experiences London dispersion forces. Okay, that's an important thing to remember. Everything experiences dispersion forces. So even something that has really strong ion-ion interactions also experiences dispersion forces. And in some cases, these dispersion forces can actually get pretty strong. So for example, iodine, this compound I2, under normal conditions, it actually exists as a solid. Whereas fluorine, a molecule that's really related to it, exists as a gas, and bromine exists as a liquid, right? So all 3 of these elements are halogens. Okay, they're all really, really related. Structurally, they look essentially identical when we think about our Lewis structures. They all look like this. So how is it that all of these nonpolar molecules exist in different phases of matter. Okay, and that boils down to the strength of the London dispersion force. Okay, without going into a ton of detail, suffice to say that really large molecules, right, the larger the molecule is, iodine is larger than bromine or fluorine. The larger the molecule is, the stronger the dispersion force. The stronger the intermolecular force, the more likely it is for a compound to be present as a solid. Okay, so iodine is a larger molecule than bromine, which is a larger molecule than fluorine. So iodine experiences the strongest dispersion forces, bromine intermediate, and fluorine the weakest. This is purely based on the strength of dispersion forces, which is based on the size of the compound. Iodine's a solid, bromine's a liquid, fluorine is a gas. Okay, so these are the three core intermolecular forces: ion-ion, dipole-dipole, and dispersion forces. Okay, they exist in ionic compounds, polar compounds, and nonpolar compounds respectively. In the next video, we're going to see two different types of intermolecular forces which are in some way a combination of two or more of these core intermolecular forces.